Hello, everyone, and thanks for accommodating me at a late hour for you guys. Thank you all for being here. My name is Divya Gopinath, and I'm a research scientist at the Robust Software Engineering Group at NASA Ames. In this talk, I will be elaborating on the research done in our group for understanding and verifying neural networks. SafeDNN is our NASA project, which focuses on providing safety assurance for autonomous systems, specifically deep neural networks, which form the core of many safety-critical autonomous systems. In the last couple of years, Dr. Corina Pesarano, my close collaborator, and I have been exploring techniques to ensure that systems that use DNNs are safe, robust, and interpretable. However, in this talk, I would be focusing on our tool called Prophecy that infers properties from neural network models. I would also be describing how we've used these properties in various applications, such as providing formal robustness guarantees with respect to safety for DNNs and robustness of DNN models, obtaining compact and formal explanations for DNN behavior, for debugging and improving the testing of DNNs, so on. So deep neural networks, or DNN for short, are machine learning models that have gained immense popularity in recent times in a wide range of applications. We see them being used for image classification, for sentiment prediction, speech recognition, as perception and controller modules in autonomous driving, so on. Given an input to the neural network function, it basically produces a prediction of the output. This could be the class that the input belongs to for a classifier, or an estimation of the values of the output variables. This is done by passing the input through layers, multiple layers of abstraction, wherein the input is represented in terms of higher level features, which are then used by the neural network to make a prediction of the output for this input. Now, each such layer consists of computational units called neurons. Each neuron takes as its input a weighted sum of the outputs from the previous layer and applies a function called an activation function on it. An example popular activation function is ReLU, which is short for rectified linear unit. This is a piecewise linear activation function. What this does is it returns a value of 0 if the input to it is negative, and returns the value of the input as is if it is positive. So despite their widespread use, DNNs face many challenges, specifically when applied in safety critical domains. The first challenge is that neural network model is basically a black box. For instance, given the following input to an image classifier, the classifier may respond saying, classifying it correctly as a cat with a probability of 98%. But beyond this, the user has no idea of why this decision was made, why it was not classified as a dog or maybe a cow. This makes it difficult to predict if the network would behave correctly on other instances. For instance, are we sure that the network would classify another image of a cat correctly as a cat? Or are we sure that the image of the horse over there would not be classified as a cat? So it's not well understood why the network makes its decisions. So there is a lack of explainability of the behavior of the network, which impacts its reliability. Secondly, unlike traditional software programs, it's not possible to provide guarantees of correct behavior for the entire network. Since neural networks, specifically those processing raw data such as images or sound waves, we cannot have a formal specification or a correctness oracle that defines what should be the correct output for any arbitrary input. It has also been shown that neural network perception models, even those which have seemingly high accuracy on a trained set or a test set, are particularly vulnerable to very small perturbations in the input called adversarial perturbations. These are like small changes made to validly classified images that are imperceptible to the human eye, which can fool the model into misclassification. For example, the street sign or the traffic light in the picture below would be validly classified to be a street sign or a traffic light, but with a small perturbation. such as just adding 11 white pixels to the image of the traffic light can fool the network to misclassify it as an oven. Similarly, the street sign could be fooled to be recognized as a birdhouse. Further, the design or the logic of a neural network is not interpretable or amenable to reasoning as against the imperative logic used to build traditional software programs. The networks are also very large, highly interconnected, often with huge input spaces, which makes efficient analysis and verification difficult. So all these factors act as big impediments for the use of DNNs, specifically in safety critical applications, where trust and certifiability are crucial. So given the challenges that neural networks face, one of the first projects we undertook in our group was to dig deep into this deep black box, or basically perform white box analysis of the network to understand it better. This led to the development of a tool called Prophecy. So given a trained neural network model, the key idea of Prophecy is to decompose the complex model into a set of compact properties amenable for analysis. Now, each such property is in the form of an assumed guarantee type rule. Pre implies post, where post is a property of the output of the network, such as the output of a classifier being a certain label, and pre is a precondition characterizing the inputs on which the network displays similar behavior with respect to post. The precondition can be formalized in terms of the outputs of the neurons of the network. We adopt such a formalization because this makes these rules amenable to analysis for many applications, such as obtaining formal proofs for network distillation. I would be talking about these applications later in this talk. In our paper in ASC 2019, we specifically considered on-off activation patterns of neurons with piecewise linear activation functions, such as ReLU. A ReLU neuron can be considered to be off if its output is 0 and on otherwise. We can consider other thresholds for this on-off categorization. However, considering binary decisions for the neurons enables a programmatic view of the network, as in the ReLU neurons can now be considered equivalent to conditional statements in a program. This in turn makes it easier to bring in concepts and techniques from traditional program analysis to the neural network domain. So given a set of labeled data, the neuron outputs or activations for each input and the respective network output is fed to a decision tree learner, which in turn extracts compact rules in terms of these neuron activations with respect to the output property as specified in post. So each rule is a path leading to a pure leaf in the decision tree, as you can see in the diagram here, and is basically a conjunction of linear constraints on a set of neurons, and is associated with a metric called support, which indicates the number of instances that satisfy this particular rule and also satisfy the output property or post. So here in the figure, I've shown the decision tree and an example of a rule which Prophecy would extract for label 0 and label 1, along with the support for those rules. So we used Prophecy to extract two types of properties. The first one being an input property. An input property is a rule where the precondition is a conjunction of constraints on all neurons starting from the first hidden layer up till the output layer or up till a certain intermediate layer. So here you could consider this rule to be equivalent to a path in an imperative program, and which basically traces convex regions in the input space. So if consider the figure on the right, on the top right, which shows an example of an input property. Here it shows that the neuron 1, 0 and 1, 2 are on, and the neuron, neuron 1, 0 and 1, 3 are on, and neuron 1, 2 is off, and neuron 2, 0 is on, and neuron 2, 1 is off. And if this condition is satisfied, then the rule states that the output label should be 0, or the value of y0 should be greater than y1. The other type of rule that, or the property that we extract is called a layer property. Here, pre is a conjunction of constraints on neurons at a single layer or a single intermediate layer of the network. Here, the intention is basically to capture the logic with respect to input features that the network uses to make its decisions. Again, there is an example of a layer property in the figure to the right, which uses neurons of the second layer. And it states that if the given activation pattern is satisfied, then the output should be label 1 or y1 should be greater than y0. To summarize, what these properties do is that the complex behavior of the neural network function on the input space is decomposed or is approximated by its behavior on multiple convex regions, either in the input space or multiple convex regions in the feature space or at an intermediate layer. So while this specifically works well for networks with piecewise linear activation functions, we've also applied it on networks with nonlinear activation, such as the exponential linear unit, on max pool layers, and we've been able to obtain rules with sufficient support specifically for the post or the output property that we were considering. So the properties extracted by prophecy have many applications. We could use them to obtain robustness guarantees. We could use them for network distillation, proof decomposition, interpretability and explainability, debugging and repair. And we've explored all these applications via case studies on perception networks, controller networks, classifier and regression models. Up till now, we've primarily considered feed-forward networks with different types of layers, such as fully connected, convolution, max pool layers, and ReLU and ELU activation functions. I just wanted to mention that in the talk, I would be using properties, patterns, or rules interchangeably to have the same meaning, that this is the rule that we use prophecy to extract from the network. So I'll first present our case study on image classification networks. We considered two popular benchmarks in image classification, the MNIST benchmark, which consists of around 60,000 handwritten digits, which gets classified into from 0 through 9. And the network we considered was a 10-layer fully connected network with 10 ReLU nodes at each layer, and also another convolution network with max pool and convolutional layers. The other data set that we considered is called the labeled faces in the wild data set, which is a popular database for face recognition networks. And we considered a data set of famous US presidents from this database. So let us consider the application of obtaining formal robustness guarantees. So properties extracted by prophecy could be formally proved on the network using decision procedure, and as shown on the slide. And if proved, these serve as assumed guarantee contracts for the network. We were able to prove 22 input properties and 8 layer properties across all labels for the 10-layer MNIST network. And we used the Marabou solver, which is a state-of-the-art solver for verification of neural network models. So an input property that we extract traces a convex region in the input space. It basically groups images that are close to each other in the input space or that look very similar to each other, and proving that all inputs in a convex region are classified to the same label proves the robustness of the network in that region. Consider the figure on the right. The first column shows images of 4, 0, and 3 drawn from the train set of the network on which the network behaves correctly, while the other images, the other columns, were generated by us from within the convex region corresponding to the input property. As can be seen, these images are very similar to the ones in the first column with minor perturbations or noise. So given that the network gave the same label for all these images, this indicates that the network was adversarially robust in the convex region surrounding the initial inputs. So remember, we didn't just prove that the network gave the same labels for these sample images, but rather we actually formally proved it using the Marabou solver that any input which satisfied the input property and was within this convex region that the input property represented was given the same label by the network. A layer property, on the other hand, represents a union of disjoint convex regions. So these represent images that do not exactly look the same, but share some common features, which makes the network give them the same decisions. For instance, in the figure on the right, we see two images of digit 4 and 3. So each of these pairs satisfy the same layer property for the respective labels. So the pairs of images don't look exactly the same, but are given the same labels by the network. So this gives us the confidence that the network has learned a higher level semantic feature of the input, which helps the network classify inputs correctly, even if they are not very similar to the digits or to the images that were supplied to it during training. So proving that a layer property holds on the network indicates the robustness of the network over the feature space. So as long as the semantic feature corresponding to 4 that the network has learned is preserved, no matter, even if there's a change in the other pixels of the image, the network would be able to identify the image as being 4 because the basic feature that it had learned was preserved. So moving on to the application of network distillation. So layer properties could also be used to build simpler networks or be used as distillation rules to save computation time. For instance, the 8-layer MNIST convolution network had a high accuracy of around 99%, but is computationally expensive, as in for every image, it takes around 7.9 seconds to process. So what we tried was we extracted layer patterns from the first max pool layer and validated each of them on a held out data set. The patterns whose validation accuracy was greater than a threshold were then deployed as experts at runtime. So whenever an input was fed into the network, it was checked if it satisfied any of these expert patterns. And if it did, then the execution of the network was halted there and the label corresponding to the expert was returned. And if none of the patterns were satisfied, then the execution would proceed as is till the output layer. So such a technique has the ability to reduce inference time, but it can also decrease the accuracy of the network depending on the accuracy of the experts. So we did a couple of experiments and we found that with a validation accuracy threshold of around 98%, the selected experts were able to provide around 22% savings in inference time with only 4% loss in accuracy. We also explored the application of patterns to debug and repair faulty neural network models. And here's a short description of what we did. So neural network models may have poor overall accuracy due to insufficient training. They could have lack of robustness on specific type of adversarial inputs, or they may have been poisoned during training, which makes them vulnerable to certain types of backdoor triggers. Now, once failure-inducing inputs have been detected, one could possibly retrain the model. However, retraining from scratch is expensive. Also, even after retraining, one cannot guarantee that the network would necessarily classify these failing inputs correctly. And it can also lead to the phenomenon of catastrophic forgetting as we start retraining it for every new failing input. So what we did was, given a set of failing and passing inputs, our tool NN Repair employs constraint-based repair to precisely fix the failing inputs by making small modifications to the network such that the behavior of the network on passing inputs is also preserved. So we used our tool Prophecy to extract rules corresponding to the correct behavior for every label at an intermediate layer. We actually chose the dense layer closest to the output layer to extract these patterns or rules. And we use these as oracles for altering the behavior of the failing tests. Given that the passing tests of the network already satisfy this pattern for correct behavior, by using them as oracles to correct the failing test, we were also preserving the behavior of the network on the passing test. We were also ensuring that the passing test still satisfied this oracle. And this also helped us localize the neurons whose behavior needed to be altered and localizing the weights which needed to be modified. So here is an example of our constraint-based repair. So this network has 4 passing tests, and out of which 2 tests have a label 0 and 2 tests for label 1. Whereas the fifth test with the input 1.5 and 2 is the failing test, which should have been classified as 0, but got classified as 1. So now if we look at the table here, which shows the activations of the neurons at the intermediate layers, we find that the neuron N2 is off and the neuron N3 is on for the passing inputs for label 0. And this is a layer pattern. This is an example of a layer property or a layer pattern that Prophecy would extract. Now, if you notice, the failing test has the output of neuron N3 as on, but N2 is also on. So it is not satisfying this layer pattern. What we do is we actually localize which neuron exactly needs a modification in its activation. And in this case, it's the neuron N2. We then we then look at the weights that are coming into these neurons. So we want to change the activation of N2 by modifying incoming weights. And we actually use an attribution-based approach to localize the weights that we want to modify. So we specifically select weights which, after modification, would have higher impact on the failing test than the passing test. And by doing so, in this example, we would select the weight corresponding to the edge N1, N2, which has a value of -1.5. So we then formulate constraints for the Z3 solver by adding a symbolic delta to this particular weight. And then these constraints are formulated for the failing test to say that the activation of N2 should be switched off, while the activations should be preserved on the passing inputs. And the solution returned by Z3 for this example is that the modification to the weight is it needs to be -1.9. And with this modification, the output label changes for the failing test, but the outputs for the passing tests are preserved. So this is just a small example of how the constraint-based repair works. And we actually applied it on a couple of benchmarks. And for the MNIST, we found that pattern-based repair helped in all 3 scenarios. That is, to improve the overall accuracy of a network, to improve the accuracy of a Poisson model without tampering its accuracy on normal test data, and also to improve the accuracy of the model on adversarial inputs. So patterns also have the potential to aid in interpreting or understanding the mechanics of how the network processes data, thereby helping with obtaining explanations for its behavior. This is because a layer pattern or a layer property potentially represents logic over input features of the input images that impact network behavior. So we extracted layer patterns for every label from the first fully connected layer of the labeled faces in the wild network, which we used for this particular application. And after extracting these patterns, we tried to visualize what input features are represented by a layer pattern by highlighting pixels in the input image that impact the neurons in this pattern. We used a gradient-based attribution technique to do this. And by doing so, this highlighted the nose of the faces to be the features that the LFW network actually uses to make its decisions. For instance, if you look on the right, it shows the images of Powell, which satisfy the same layer property, and also the input pixels, which get highlighted for every image. These are the pixels that impact the neurons in the pattern. And we find that, no matter where the face is looking or whatever mood he seems to be in, the nose seems to be the feature that makes the network guess that it's Powell. Similarly for Bush as well. So such information could also be used to debug or improve face recognition networks. As in this case, one could possibly just overlap the nose of another person and then fool the network to be recognized as somebody else. So this helps us understand what the network is actually looking at to make its decision. So I will now move on to present our case study on a controller network. ACAS-XU is a set of neural network models which is used for collision avoidance in unmanned aircrafts. Each network takes in 5 sensory data as inputs, such as the range between the own ship and the intruder, the speeds of the own ship and the intruder, their angle, so on. And it produces as output horizontal turn advisories to avoid conflict. So this could be either clear of conflict, strong left, strong right, weak right, so on. And the network that we used had 6 layers with 50 ReLU nodes at each layer. The ACAS-XU system, I'm going to explain how we explore the application of proof decomposition and specifications in inference for this particular controller network using our patterns. So the ACAS-XU systems has domain level specifications provided by the domain experts, which are in the form of an input-output specification as shown. So it has A implies B, where A represents a predicate on the input space and B is a turning advisory. And we found that proving these input-output properties on the full network using ReLUplex, which is again a state-of-the-art solver for neural network verification, consumes a lot of time and many properties would time out without getting proved. So what we did here is we try to extract layer patterns or patterns at an intermediate layer of the ACAS-XU network and try to use them as interpolants for decomposing these proofs. So we would basically prove A implies B by using a layer pattern by checking if A implies the layer pattern and the layer pattern implies B. These two could be separately checked using ReLUplex. And we found that by such a decomposition helps up to 75% increase in speed of solving or proving these properties. And we were also able to check some properties that timed out with monolithic verification. The other application that we tried with ACAS-XU is specification inference. So ACAS-XU, unlike perception networks, where the inputs to the network are raw image pixels, this particular controller network has more meaningful input variables. So the input variables have more semantic meaning pertaining to the domain, as in they are the range, they are the speeds of the on-chip intruder, so on. So representing layer patterns in terms of the input variables leads to the discovery of specifications of the domain. So for the layer patterns at ACAS-XU, we discovered novel input-output specifications as shown on the slide. And these were actually validated by the domain experts to be correct for the ACAS-XU network. So moving on, let's now consider a regression model used for perception-based control. And I'm going to explain the case study we did with this particular network. So TaxiNet is a neural network which is used for autonomous centerline tracking in aircrafts. The network basically takes a single picture of the runway as input and returns the plane's position with respect to the middle of the runway as output. It basically returns 2 numeric outputs, which is the cross-track error y0, which is the lateral distance of the plane from the centerline, and a heading error, which is the angle of the plane with respect to the center of the runway. We basically considered 2 networks, an ACT or an autonomous centerline tracking TaxiNet, which was provided by our industry partner, and another academic smaller network called KJ TaxiNet, which is a smaller network with ReLU activations, but has almost similar accuracy as the ACT TaxiNet network. And our goal here was to use the patterns extracted by prophecy to understand or explain the behavior of this regression model, provide robustness guarantees with respect to 2 properties of the output. So here it's a regression model. So we have different properties as against the classification models that we have been seeing till now. So one of these properties is a correctness property, which basically checks if it uses error bounds or a difference between the ideal expected output and the actual output of the network to determine if the network is giving correct output or not. And then we will also check safety properties, which basically uses the runway dimensions to indicate if the plane is under safe operation. So we use prophecy to extract patterns with respect to these two properties. So we basically use these patterns to explain correct and incorrect behavior of the model. So prophecy was used to extract activation patterns with respect to the satisfaction and violation of the correctness property for the ACT taxinet. So here I give examples of two such patterns. The first is an activation pattern for the satisfaction of the correctness property with respect to the cross-track error y naught. So as shown, if the following activations pattern is satisfied, it implies that the difference between y naught and y naught ideal, which is the expected output for y naught for that particular input, is less than equal to 1.5, which is like an error threshold. And an example activation pattern for the violation of the correctness property is as shown, which implies that the difference is greater than 1.5, which is like an error threshold. So as I explained earlier, we tried to visualize the features, the input features that were represented by these patterns. We use the GradCam++ attribution technique to identify pixels of an image impacting the neurons in the pattern. So given an image that is satisfies the pattern for correct behavior, we identified the pixels and highlighted them using GradCam++. Now, a difference that we did here with respect to the other case studies is taxinet network receives input images in a sequence as the plane moves forward on the runway. So hence a sequence of images satisfying the same pattern represents actually an interval of time over which the network displays same behavior on the inputs. So instead of looking at important pixels on a single image basis, which sometimes could have some noise, we actually averaged the GradCam values over all images in a sequence satisfying the same pattern to visualize the common feature that impacts the network behavior for a given scenario or over a given time window. So for instance, consider the picture on top right. This represents a sequence of 10 images satisfying the pattern for correct behavior. We show the min and max images from the sequence in order to highlight the range of the values the pixels can take in this scenario. We then summarized or averaged the GradCam values, and here is an image of the summary of important pixels for this particular scenario or for this particular sequence. So this indicates, as we can see that the portion of the image in between the center line and the nose of the plane gets highlighted, which indicates that the network used this feature to estimate the cross-track error. And this is correct because the cross-track error basically should represent the lateral distance between the plane and the center line. So this helps us understand why the network behaves correctly for this scenario. On the other hand, look at the sequence of images satisfying the pattern for incorrect behavior. Here, most part of the image seems to be highlighted or seems to impact the neurons in the pattern. This shows that the network is unable to localize a feature or use relevant information from these images to make a correct estimate of the cross-track error. We also tried to prove layer patterns or try to provide robustness guarantees. But on the ACT network, we were unable to apply the existing Marabou tool to prove these properties because it doesn't work with ELU activations. So in order to explore this application of robustness guarantees, we considered a smaller fully connected network called KJ TaxiNet, which has ReLU activations, but has almost similar accuracy as the model from the industry partner. So we used prophecy to extract activation patterns with respect to the satisfaction of the safety property for the KJ TaxiNet. And we employed Marabou to prove these properties. Again, we leveraged sequence of images satisfying the same pattern to determine intervals of time under which the network is under safe operation. And this is the exact formula that we checked. So we checked that for all inputs which lie within an xmin xmax. Now, what xmin xmax indicates is it's like an over approximation box that we constructed in the input space based on all images that satisfy the same pattern in the sequence. So for every image within this approximation box, if the pattern of the network is also satisfied, we wanted to prove that the safety property with respect to the cross-track error was satisfied. So we obtained proofs for 33 sequences with at least 5 images, and the longest sequence had proof had 17 images. So another thing which helps, which was a result of these proofs, which would help us, are the counterexamples. So let's say if some of these didn't get proved, the counterexample to such a proof is an image which is similar or to other valid images in the sequence, but violates the safety property. So as shown in the picture here, so it basically shows scenarios or a sequence of images which satisfy the safety property. And when we tried to prove them, we obtained an image which violated the safety property. Now, the third image in each of these, in both these pictures, is the representation of the counterexample in a downsampled input space. Basically, the KJ taxinet, the way it works is by downsampling the input images to a smaller domain, to smaller dimensionality. This is how they build a smaller network to work for the same application. So we also show the since the proofs are carried out in the downsampled input space, we get the counterexamples in the downsampled input space, but we then mapped it back to the original domain, and the last images in each picture represent these counterexamples. Lastly, let's look at a case study on an object detection network. So SqueezeDet is a state-of-the-art network for object detection in autonomous cars. It basically receives as input images from the camera on the car, and it is supposed to detect obstacles or objects in front of it. Scenic is a recently proposed probabilistic programming language which can be used to describe environments or scenes for testing networks in autonomous driving. A scenic program can be used to specify values of environment variables describing a scene, such as the weather conditions, time of the day, position of the vehicle, so on. And these variables are in turn fed into a simulator to create realistic images for testing the network. So what we did here is, given a set of passing and failing tests for the object detection network, we employed prophecy to extract patterns for correct and incorrect behavior. And the rules, which are actually in terms of neuron activation patterns, we tried to map them back to high-level semantic features. So the way we did this is the environment features or the environment variables from the Scenic program corresponding to each test were recorded. And the images were bucketed based on the patterns they satisfy. And then we applied decision tree learning to extract rules in terms of the features of the images, or in terms of the weather conditions, basically the variables that the Scenic program supplies to the simulator for a particular image. So the rules in terms of high-level features act as better explanations, more understandable explanations for correct and incorrect behavior. They're more meaningful than attribution at pixel level, which is typically what has been done for perception networks. So here's a diagram that highlights this idea. So for a given scenario specified in the Scenic language, let's say we have some failing test images and some passing test images, we used our technique to generate rules in terms of high-level features for the failures and for the success. So here the failure inducing rule that we extracted was that the x coordinate, or the position of the car, is less than equal to minus 200.76. The distance between the ownership and the obstacle was less than 8 meters, and that the car model was Park Ranger. So similarly, we extracted a rule for the success cases, which stated that the x coordinate was greater than equal to minus 198.1. So the way we used these rules was then we used them to refine these scenic programs, which enable the generation of more number of failing tests and passing tests. So these additional tests could be used for debugging the model or retraining the object detection model. This is an example of how we used our patterns for extracting more semantically meaningful explanations for an object detection network. So to conclude, I just want to go over the work that is in progress and what we have planned for the future. So we are looking into using the patterns that we extract from the intermediate layers of a neural network model as runtime monitors. So let's say we extract patterns for incorrect behavior or correct behavior. We extract these offline using a set of labeled data, and then we deploy them at runtime and monitor for abnormal behaviors or deviations from expected behavior, and flag them, or you basically use them as runtime guards. We are also exploring structural coverage metrics for neural networks, and we believe that patterns extracted by prophecy have the potential to capture behavioral, functional, and feature level coverage. So we want to use patterns as a metric for structural coverage to assess the adequacy of testing neural network models. There's a lot of existing work on this, but that basically uses notions of like neuron coverage, or a basic activation coverage, or some threshold coverage of neurons, which makes sense in a structural view, but it's not clear how it maps to the behavior of the network, or the various functionality of the network, or more importantly, the feature which the network is using to make its decision. So we believe that activation patterns, which are specifically extracted based on certain output properties, have more potential to capture feature-based coverage, functional coverage, and behavioral coverage. And we are also looking to see how we could extend this work to recurrent neural networks, and what sort of benefits the patterns from recurrent neural networks could provide, and how we could use them to analyze recurrent neural networks. Thank you, everyone. This is just a short description of what we've been doing at the SafeDNN group in NASA Ames. Thanks for your patience, and I'm open to any questions.
Great, thanks, Divya. Clap. We'll try and make it feel like it's a real conference. So thank you so much for the really interesting talk. If anyone has questions, please put them in the Zoom chat or in the Slack as well. And if anybody in the room has any questions, just put your hand up, and then you can ask me, and then I'll say it through the microphone, because we're still not completely, we can't do all of the technical stuff. So yeah, thanks again, Divya. I have a few questions in there already. So the first one is from Anubhav. It says, is it possible to detect if an image is perturbed even before it is passed to the classifier? And can we formally verify this detection process?
Thank you for the question. So as in, do we want to, is the question that can we use prophecy to detect if an input has been perturbed before passing it to the network? Is that the question, or?
I think so.
Yes, actually,
yes.
Yeah, so let's assume that we applied prophecy. Let's say we have a set of adversarially perturbed images and correct images offline. We could use prophecy to extract patterns. So basically, prophecy is doing white box analysis of the network. So it wants to make a decision about an input based on what the network does with the input. So it's not just looking at the input, but it's looking at how the network processes the input. So let's say there is a pattern for which was satisfied by most adversarial inputs in the past, or maybe from the, from an adversarial set that one had offline. And at runtime, you got an input, and then that satisfies this pattern, then we could just flag it saying, we think that this is potentially adversarially perturbed. So prophecy could be used to identify such inputs, but then it would actually execute the network until it reaches the layer at which we have this pattern, and then it would make the decision. So it will not do a black box analysis of just the inputs.
Okay, great, thanks. The second part of their question, I'm not sure if you've completely answered it. They've asked, can we formally verify this detection process? So can you formally verify the prophecies process?
Yeah, so we try to formally verify that the patterns extracted by prophecy are provable on the network. So we were able to do that for the MNES network and also for the KJ TaxiNet network using, so to formally verify this, we are relying on the state-of-the-art solvers for neural network verification, and we use the Marabou solver, which works well for ReLU activations and fully connected networks. So we were able to formally prove these properties on some networks.
Okay, cool, thanks. The next question is from Sasata, and there's actually 4 of them. So I'll just go through them each individually. So the first question is, can DNNs be modeled using any logic? If not, then how can the guarantees be trusted to be logically sound?
So as I said, we are trying to, so the DNN is actually a complex nonlinear function on the input space. But what we are doing is, let's consider a certain property of the output. And with respect to that property of the output alone, let's say if for the classification to label 0, can we approximate this nonlinear function over multiple convex regions in the input space? And these convex regions could be at the input layer or at an intermediate layer. So the decision tree is basically just a conjunction of linear constraints on these neurons. So we are trying to see if we can use these as boxes of convex regions, and can we approximate the behavior of this huge network on these convex regions. And just for that, we are trying to prove. So we have multiple patterns which work for their individual convex regions, either at the input space or at the intermediate layer, and we try to prove them. We're kind of breaking down this complex nonlinear. So we are not giving a proof for the entire network. It's an assumed guarantee type rule. So for a given convex region, we are proving a certain behavior of the network on that convex region. So it's an approximation. We're not proving the behavior of the network on the entire input space.
Thanks. So the next question is actually related to what you've just said. If only compact properties can be verified, are the resulting guarantees useful in the bigger picture if they cannot be used to guarantee something about the complete DNN?
Yeah, so we did, as I explained, there are many applications of, even if we are not able to prove, I don't think we can provide a guarantee for the entire network, especially for perception networks, because there, as I said, there isn't a correctness. What would you check the output against? There isn't a correctness oracle for any possible input. But even these smaller compact properties, we use them to say that there are these pockets where the network is robust. There are these features over which the network is robust by proving the layer patterns. We also use them for explainability by mapping them to input variables or mapping them to higher level features, semantic features, to understand why the network is giving decisions, at least on certain convex regions or certain input, certain sets of inputs.
Okay, the third question says, are the guarantees data dependent? Will they hold on arbitrarily unknown data?
Okay, so yeah, we are using a set of label data. Now, this could be the train set for the network, or any arbitrary label data to extract these rules. But we are using decision trees, and we are extracting rules so that they don't overfit to the data that we are using to extract these patterns. So given that they are compact and they are being extracted by the decision tree learning algorithm, we hope that these would be generalizable. And the way we do this is we construct the decision tree, extract rules, pure leaves with high support on the label data, but we also validate them on a held out validation set. We also try to prove them. If we prove them, then we know that it's valid for any data. But in the event that we are not able to prove them, we use a validation validation accuracy of those rules on a held out data set to give an idea of the generalizability of these rules.
Great, thanks. So Swata's final question is quite broad. And they've said that given that black box systems can never be completely modeled, in your opinion, is it safe to trust them without some degree of skepticism for safety critical applications?
So for safety critical applications, we can definitely trust the patterns that were proved. Number one, we can just trust them because we proved it on all possible inputs in that particular convex region. And the other major application is the runtime monitoring, right? So you could use them as guards with a certain level. So when there is an input, given that you have this layer pattern, which was satisfied by a maximum number of invalid inputs or wrong inputs in the past, you could flag these inputs. And or you could say that the confidence of the network's output on these inputs is very low. So it could also be deployed in that manner if you are not able to prove these layer patterns.
Great, thanks. So Fata asks a question about Marabou and prophecy. Specifically, they have issues in understanding what prophecy is used for exactly and what is the performance of this method using Marabou and prophecy compared to just using Marabou as a verification tool.
Yeah, so the way we used prophecy was to simplify the verification of input-output properties. So we used Marabou to verify input-output specifications of the ACAS-XU network, and we found, we compared the times. So there were some properties which timed out after 12 hours using just monolithic Marabou verification on the entire network. But when we used the layer patterns and kind of did this in a compositional manner, that is, we would prove if the layer pattern indicates the output property on a smaller network, because the layer property is at an intermediate layer. So the number of layers that you need to include for this proof is just the second half of the network from the layer at which the property was extracted till the end. And we would then try to prove if the input predicate in the input-output specification would imply this particular layer pattern or would imply a set of layer patterns. And then if that is the case, then you actually, it facilitates more efficient use of Marabou to prove these properties.
Great, thanks. Nicholas has one question. He asks, could you give some insights about the complexity of pattern identification?
So it's just the complexity of the decision tree learning algorithm. It's the same as that. So we are just basically executing the label data on the network, recording the neuron activations at the different layers, and invoking the decision tree learner to generate compact, to extract these rules. So it would be at the order of the neurons at that particular layer, but decision tree learning is the fastest learning algorithm to extract these rules.
Great, thanks. So we're through all of the questions in the Zoom chat at the moment. And are there any in the room? No? Are there any on Slack, Matt?
Nothing on Slack.
No. We're multitasking here, Divya. It's a really entertaining setup.
I can ask a question.
Matt has a question.
Which, yeah, I don't know whether so you can repeat. Basically, it's going back to standards and regulators again. So I was wondering what what's the link between the output of the tools she's been talking about and what regulators or standards expect you should system?
Okay. Did you hear that, Divya?
Yes, yeah.
Microphone is better than we thought.
So actually, the standards for machine learning algorithms is, still being discussed for safety critical applications. FAA is looking into it. There is some guidelines from EASA, the EASA guidelines. They talk about having explainability. They talk about traceability to requirements. All this, it's very clear how we could do this in a traditional software program setup, but for machine learning algorithms, I think we are actually working to see how we can make this mapping. But some of the ideas we have is the coverage thing that I was talking about. So in software programs, if you just give a report of the MCDC type coverage of a software used for of flight software, that suffices to satisfy the standards for trusting the software. But here in a neural network, given that it's a different beast, it's not an imperative, it does not have a logic similar to a software program. So does this mean that an MCDC coverage of all the structural components of a neural network is enough to trust it? We don't know, but we have a tool which measures MCDC coverage, neuron coverage on neural networks, and we also want to build the patterns as a coverage metric, right? So let's say I have an activation pattern for a certain label. So by having tests covering this particular pattern, we know that there is functional coverage for that in the test suite for that particular label. Similarly, we could say if there is a pattern for correct behavior and incorrect behavior, we should have tests which cover the patterns for incorrect behavior, so which maps to the defect detection ability of the testing. So also maybe patterns could be mapped to higher level semantic features, which in fact may be included in the requirements for neural networks. Because for perception modules, the requirements are very different from software, a software used for perception, right? Like a traditional program. Here, the requirements might be in terms of semantic features. And if we show that there is a coverage of different features, semantic features, then that kind of enables a traceability between the requirements and what the neural network is doing. So these are some ideas, but this work is still going on in trying to actually map this for neural networks.
Great.
Thank you.
We have two more questions. So the first is from Nicholas. He says, any idea for combinations of patterns with abstract domains like deep poly, for instance?
I'm sorry, I'm not aware of deep poly, but if you could expand on this abstract domains, I could try to answer. Or
okay, there's another question, so we can move to that, and if Nicholas wants to clarify, he can add to the chat. So the next question is from Barak, and his question is, has NASA fixed any actual problems in a network using these methods?
Well, we have caught some problems in the KJ TaxiNet network. We also caught some problems in the autonomous Centerline tracking network supplied by our industry partner. As in, we used patterns for incorrect behavior, and we passed it on to them, and they were able to analyze scenarios where the TaxiNet was not working properly. But I need to mention we were not given the actual model which is under operation. We were just given like a toy network which does the same thing for our use. So it has not been, if you're asking me if it has been used in some actual mission critical application on the field, then no, it's still under the umbrella of research.
Okay, great. I think we're probably just time up. Oh, hang on, Nicholas has clarified, so I better come back to him. He says, deep poly is related to the verification of robustness via abstract interpretation techniques. The idea is to compute complex regions of neuron activations at hidden layers of the network. And his question was, have you any idea for combinations of patterns with abstract domains, like deep poly, for instance?
Yeah. I think that we haven't looked into a relation, but I think the idea is pretty similar. But given that deep poly does abstract interpretation, I'm trying to think whether there would be any approximations, because here the patterns that we extract are directly from I don't know, maybe it's too soon to comment anything, but I think there's a possibility of a combination here. Thank you for pointing this out, Nicholas. Thanks very much.
Great. I think we'll leave it at that. Thank you again, Divya, for a really interesting talk and, really hot topic in the area of autonomous systems. So thanks again. We'll clap.